papers on different security topics, and they also have some petitions, and we also release some tools that I'm going to speak about them later. So Shellphish started in 2004 at the Center of California Santa Barbara, and it's a nice place, but we like to stay inside the building from the monitors. And so then Shellphish expanded to other places such as Northeastern University, that as you can see it has a very different weather, and and so we have Shellphish in the last year. We have the people playing with us from all over the world, and we just meet people from Australia. So if you know someone from Australia, that would be nice. But so, as I said, there is a good competition. Typically for CDF,
Comment tu sais ce qu'il y a dedans?
Hier, on m'a sorti la traduction française de To Spoil. Petit peu caché. Petit peu caché. Je trouve ça génial.
Ouais, c'est pas mal. Bon, métier.
So as I say, it started in 2014. Qualification events was about 1 year ago, and now and 7 teams qualified for the final event. It will be August 4th at DEFCON. That is the huge security conference in Las Vegas. So CGC, it is the abbreviation of DARPA Cybergun Challenge. CGC is an attack defense CTF, but instead of players, instead of solving security challenges, they have to develop a system that automatically solves these challenges. And so the focus here is, of course, on automation, and in particular what you have to do is to exploit vulnerabilities in binaries. So you are provided with some binaries, you need to you have to develop a system that is able to automatically find vulnerabilities in these binaries, but also to patch these binaries. It means to correct the vulnerability that allow exploitation. And as I say, no human intervention is possible. So everything has to generate exploits, and what is the real meaning of exploit? What is the precise definition? So for the qualification round, an exploit was just something that it was just an input that when provided to the binary was crashing. And also patch the binary. So what is a patch? A patch is a fix to the binary.
C'est sympa, t'as vu, ils ont bien cendrier.
Okay. A patch is a fix to the vulnerability, and you need to preserve the original binary's functionality. So you cannot just change your binary so that it just returns, because if your binary just returns, okay, the binary is not exploitable, but the functionality is completely corrupted. And also performance impact of these patches is evaluated, so that, for instance, if your patch, maybe your patch is checking all possible memory accesses, but you might end up in having a too big CPU overhead, and so the evaluation of your patch will be low. So for CGC, the binaries were provided for CGC, they were more or less heuristic programs, but they run in a simplified environment, with simplified system calls and simplified inter-process communication. In particular, the architecture was standard Intel x86 32-bit, but these binaries are supposed to run in an operating system called Decree, that is just let's say a simplified version of Linux, where you only have 7 syscalls. Like, you can transmit, receive data on different sockets, and you can select on these sockets. You can allocate memory, you can generate random numbers, and you can terminate. So that's it. So there are no signals, no threads, no shared memory, not even a file system. And also standard defense techniques that are usually in place in modern operating systems are not there. So the stack is executable, there is no randomization, and so you are free to implement these defenses as a patch to the binaries, but of course you need to also consider the performance impact these patches are bringing to those binaries. And also, of course, you need to do it in a way that your binary functionality is not compromised, so you need to do it very carefully. And so this is just an overview of what we developed for the qualification rounds. So for the qualification rounds, we were provided with vulnerable binaries, and our system, that in DARPA terminology is called a cyber reasoning system, our system was supposed to, as I said, provide exploits and patch binaries. So this is a little bit more detailed view. So vulnerable binaries were passed to automatically a vulnerability finding component and to an automatic patching component. So the vulnerability finding component was generating proposed exploits, and then these exploits were going also to the patching component, because some of the patches were targeting the specific exploits. And then we output both proposed patches, and both exploits and patches are evaluated, And of course, we pick the best one, so the most reliable one, and the one with less performance impact, and we submit those exploits and those patches to DARPA for scoring. So, as I said, one of the components we developed for the CGC was an automatic vulnerability discovery component. And so, I'm going to introduce how you can develop a system that automatically finds vulnerability. So, for the qualification round, the question we wanted to answer was, how do I crash a binary? Because for the qualification, an exploit was just an input making the program crash. So this question is somehow a subset of a bigger question, that is, how do I reach a specific state in a binary? And so this in general is not decidable question and not decidable problem, but there are two approaches that more or less can give you an answer, at least in some cases. So one is called fuzzing, and the other is called symbolic execution. So let's see both of these approaches. So I put some code. It's just an easy program that gets an input from the user, checks two conditions of this input, and then it either prints a you win or you lose. And suppose that we want to answer the question, how can I reach the state in which you win is printed? So, of course, an easy solution is just to try different numbers. So you try 1 and you lose is printed. You try 2, still you lose is printed. But if you try 10, you win is printed, because 10 verifies both conditions. And so this is a very easy way, so to speak. And in particular, for CGC, we use a particular type of fuzzing called coverage-guided fuzzing. That means that our system were focusing on those inputs that cover the binary, so those inputs that execute more instructions inside the binary. And our system was based, and is based on AFL, that is a very famous public fuzzer. And fuzzing works very well in a lot of cases, but there are some specific cases in which fuzzing does not really work. And let's see one of these cases. So suppose that now I change the second condition to from x less than 100 to x squared equal to a big number. And so now if I try random inputs for my code, it's very unlikely that just by trying random numbers I will be able to print, to reach the condition in which the text you win is printed. So a different approach is called symbolic execution. So let's look at how symbolic execution works in the original example and how it works in this more complex example. So the idea of a symbolic execution is to interpret the binary code and replace any user input with symbolic variable. So at the first instruction we have user input, and so we don't know the value of this input because it's coming from the user. So we just keep track of it as a symbolic variable x, and then the execution goes on. And of course, if we encounter a branch instruction, we don't know which one of the two branches we are supposed to take because we don't know the real value of x. So we take both branches, but we keep track of constraints that those conditional instructions are imposing on the execution. So for instance, in one case, the constraint is x bigger or equal than 10. In the other case, the constraint is x less than 10. So the execution goes on, executing all the feasible paths. And for instance, if we execute the path in which x is less than 100, we add the constraint x less than 100. So then, at some point, we will reach the condition we were looking for, that is the text you win is printed. And so now we ask to the symbolic execution engine to give us, to concretize the collected constraints. That means to give us a concrete input that satisfies these constraints. So we collected two constraints, x bigger or equal than 10 and x less than 100. So a possible solution is 99. And in fact, if we try 99 as input to this program, we will reach the condition in which the text you win is printed. So if we move from the simple example to the more complex one, we see that for symbolic execution, this is just a matter of having a slightly different constraint. So now we have the constraint x squared equal to that big number, but still a symbolic solver can still provide us a solution to this problem. And in this case, the solution is x equal to 1, 2, 3, 4, 5. So we use symbolic execution for CGC. And in particular, we use symbolic execution from Anger, that is this binary analysis platform developed at UCSB. And in particular, so we were looking for inputs that were making the binary crash. And so we were looking, for instance, for memory accesses outside allocated regions or unconstrained instruction pointer. That means a state in which the instruction pointer of the program can assume any value. For instance, we have some user input going to a register and then jumping to that register. So in that case, the instruction pointer can assume any value. And so if either the condition 1 or condition 2 is true, it means that we found an input that will make the program crash. That is what we were interested in. And so we also studied how to merge the two approaches. And in particular, our lab published a paper called Driller that has been published on the NDSS February 2016. And this paper studies how to merge these two approaches. And what is interesting is the following. If these are all the binaries we were provided for the qualification, these are the binaries that we were able to find the crash using just fuzzing. So this is in scale. And these are the binaries we were able to find the crash using symbolic execution. But combining the two approaches, we were able to find more than just the sum of the two approaches alone. And you can find details about this in the paper called Driller. And okay, so as I said, our symbolic execution and also Driller are based on Anger, that is the binary platform developed at UCSB. So I'm not one of the developers of Anger, so if you have super technical questions, I'm not sure I can answer. But anyways, Anger is an open source project. You can find it on GitHub. Please put a star. And it's an architecture-dependent system, and of course, it's compatible with normal ELF, with CGC ELF, but also with Windows and other architectures. And it's written in Python, so it's allegedly easy to use, and you can install it with one or maybe two different commands, at least on Ubuntu 14. And you can interact with it using IPython, like an interactive shell. And so now I'm going to show you a demo of how we can use Anger to, in this case, to find an input that makes a program crash. So I'm going to show you how to apply Anger to this binary called cadet1. It is a very easy sample binary DARPA release for CGC. And what this binary does is just checking if a string is a palindrome. So we can run it here. So I can put any string, and it will tell me, no, this string is not a palindrome. If I put a palindrome, this binary will tell me it's a palindrome. So the reason why I'm using a dot adapted version is because this is a CGC binary, so and this is a Linux machine. So to run it on a standard Linux machine, we had to recompile it. So this binary has a classical buffer overflow. In particular, 128 bytes are read from user input, and they are placed in a 64 bytes buffer. So an attacker can exploit this to corrupt the memory, in particular to write some data on the stack. And so through this, you can hijack control flow and having basically arbitrary code execution. So how can Anger find this condition? Let's see. Okay, so we can open IPython. So we import Anger. and we can create a new project. So now we have a new project. So what we want to do is to create a path group. So a path group is basically a data structure used to hold all different paths that the symbolic execution discovers during the execution of this program. So we need to do this. I'm gonna copy and paste. So we just do basically project.pathgroup, and we need this option save unconstrained, because in this case we are specifically interested in unconstrained paths. That means that the user input control the execution of this program. So now we can just step the program just to see. So if we step, we see that the path group contains one active path, and if we see the path, it means that we have our execution is at this address, and if we look at that address in IDA, we'll see that that address is just the entry point of the binary. We can do another step, and we can see that now we are at this other address that is the second basic block of the binary. So you can use Anger just to execute a binary, but as I said, in this case, I'm interested in finding an input that makes the program crash by reaching a state in which user input controls the instruction pointer, and this state is called an unconstrained state. So what I can do is I can just do an easy while loop. So in this while loop, I check if the length of the list containing unconstrained paths is bigger than 1, I exit. Otherwise, I just step. So now it's stepping. It should take 10 seconds probably, and at some point we are gonna get an answer, ideally, hopefully. Okay, so now it means that Anger found an unconstrained state. We can actually save this state in a variable, and then what we can do is we can dump the content of std in this state. It means that we can dump what the user is supposed to input into this binary to actually reach this unconstrained state. So we do state.posit.dump, 0 is std, and we save it in a file. Okay, so now if we look at the content of that file, we see that it's basically just a lot of null bytes. And as a matter of fact, if we cut this file into the program, the program crashes with the segmentation fault. So that's good, because this was something like this is a valid exploit for the qualification. And I'm going to show you another example of how you can use Anger. So this binary also has an Easter egg. So this is the code that I use. You can use it. You can get it from the slides later. So an Easter egg. So it means that if you input a string starting with that accent character that is called caret character, if you input a string like that, the text Easter egg is printed. We can actually try this. And if we input something like this, the text Easter egg is printed. So we can ask Anger to actually, without knowing anything about this binary, to actually give us an answer about how we can reach this Easter egg. And so, okay. So in particular, what we can do, if we look at the binary, for instance, in IDA, we see that when we reach this instruction, the Easter egg is going to be printed. And so we ask Anger how to provide us an input that when provided to the binary, that instruction is going to be executed. So this is going to take some time, so I'm going to start it and then describe it. Okay, so these are the instructions I just pasted. So as before, you input Anger, you create a new project, and then you need to basically disable this option so that you use less memory. And okay, you can find all the details about this in the documentation. And then, as before, you generate a path group, and then you just call pathgroup.explore. You put the address you want to reach, and then eventually you will find a state. A state that means a state in which you have an input that is actually reaching that instruction. So this is going to take a while, so maybe I can go on and then show it to you. Right now, Anger is doing computations, and he's also complaining because it found a state in which, basically this means that it found a state in which the instruction pointer is unconstrained, because this program is actually vulnerable. So Anger is somehow an anomalous condition, so it's giving this as a warning to us. But I think it should be done in 30 seconds, maybe. Let's see. Maybe more. Anyways, let's go. Let's wait. Okay, so it reached a state, it saved the input in this file. So if we look at that file is actually starting with a character as expected. And if we cut that file into our binary, we'll see the Easter egg. So see, the Easter egg is printed. So these are just two easy examples. You can find tons of examples in the Anger repository called AngerDoc, including this example. And also you can find how Anger can be used to solve a lot of different CTF challenges. That is probably the main usage right now of Anger, except from CGC and for papers. And so let's speak about the finals of the CyberGrant challenge. So 7 teams qualified for the finals. Shellphish is one of them. And in particular, we exploited 44 binaries out of the 131 binaries we were provided with. And every qualified team received $750,000. That is good to have. And so you can read, so basically, I didn't speak about patching much in this talk, but if you're interested into patching, all the team submissions for the qualification, you can find them on that link. And if you like doing reversing, you can just reverse all of them, and you can study how different teams implemented patches differently, how they injected code inside binaries, and also what did they try to defend with these patches? Did they try to just do some specific checks? Did they try to check all the memory accesses? It's pretty interesting to do. But there are a lot of binaries, so it's a long work that, of course, we partially did in preparation of the final event. And so in the final event, the setup will be a little bit different. So it will be a round-based attack defense CTF with zero human intervention allowed. And because in a qualification, we were not allowed to look manually into binaries and to find manually exploits for them, but we were allowed to, for instance, fix bugs in our infrastructure. For the finals, we will not be allowed to fix our infrastructure, so we need to have a system that is able to run for hours, synchronizing different information without any human intervention. So that's pretty scary because, of course, maybe we miss a semicolon somewhere and everything will crash and we will get 0 points. So there is a lot of testing we are doing, like a lot. Like every commit is tested. There is a lot of infrastructure just to test everything. And also during the finals, data about previous rounds is available to your system. So basically, you can receive network traffic that other teams are sending against your binaries. You can also get patches that other teams submitted. And so it can even be possible to steal patches from other teams or to study network traffic to somehow steal exploits. So this brings to a lot of questions on how maybe you should not immediately deploy a patch because maybe someone else could steal it. There is a lot of metagaming that, of course, different teams will probably implement in different ways. So also exploits are different. So for qualification, an exploit was just a binary, an input making the binary crash. For the finals, an exploit will be either an input that makes the binary crash, but at a specific location, and also setting a given register to a given value. Or an exploit can also be an input that, when provided to the binary leaks some information, some data from a specific memory page. And so because of this, we need, of course, a more realistic exploit generator, with just something that tells us how to crash the binary is not enough. We need to move from a crash to a real exploit. In addition, on top of all of this, every team could also deploy network-level filtering rules that are just network-level rules that you can deploy so that you can stop traffic from reaching your binaries at the network level. So as part of the finals, every team has access to a cluster of 1,280 cores, 16 terabytes of RAM, 128 terabytes of storage, and this is basically a rack of one for one of the team. So DARPA is bringing 7 of these guys inside an hotel in Vegas, and I think they're also bringing a 0.5 megawatt generator to power all of them and to cool them. So this is going to be interesting. And of course, when we got access, the first thing we did was HTOP, and then we did HTOP on all of them, and it took us like probably 2 hours to generate this screenshot. And what else? So finals will be at DEFCON in Vegas, August 4th, so it's less than 1 month. And there will be money prizes. So first team is gonna get $2 million, second team is gonna get $1 million, and the third place will be $750,000. And also, the winning team will compete against human teams at the standard DEFCON CTF. So this means that this year, DEFCON CTF will be in a CGC format, and so that the machine and the humans could play together against each other. And this also means, and if I understood correctly, the winning team will have access to the entire 7 clusters, so it's going to be something like 100 terabytes of RAM and 10,000 cores, something like that. So that is going to be very interesting. But of course, we don't know who will be the winning team. And what else? Let me just finish with this, a picture of all of us that work for the qualification. And as you can see, we are people from all over the world. And this is a picture of us working at the finals. And with this picture, we achieved 2 goals. So first of all, we all look very weird, and also Italians pass Americans. And so with this, I'm ready to answer to your questions.
Thank you very much, Antonio. Do you have any questions in the audience?
I'm giving you a free T-shirt for a question. You want a free T-shirt? Or you just want a question?
Oh, free T-shirt given.
So you can find the slides there, other information.
Hi. When the script that showed the single stepping, what performance are we to expect from that?
From what?
The single stepping, one step to the other. What kind of impact does it have on performance?
During, sorry, I didn't get it. During symbolic execution?
When you were doing this symbolic execution, if you go back in the script.
Yes. Okay. Which kind of performance?
Yeah, what delay does it have? If I execute the executable and then I execute it with anger.
So if you do just symbolic execution, you are, especially because this is in Python, is probably going to be hundreds of times slower than a normal execution. And let's say that there has been a lot of research on trying to avoid of just doing blindly symbolic execution, but as I say, to mix fuzzing that is like normal execution with symbolic execution only when it is needed. So, but yes, symbolic execution is very slow, And even more, the biggest problem is memory. Because you need to keep track of all the paths you are exploring, and of course, when you have a branch, you don't know which path to get, you need to keep track of 2 paths. But then if this branch is inside the loop, you get to what is called an exponential explosion of paths. So yes, symbolic execution in itself is not very efficient, for sure.
And what solver are you using?
So Anger is using VEX to transform assembly instructions to an intermediate representation, and then VEX, the solver is Z3.
Okay.
Yeah.
Okay, thank you. Very good presentation.
Okay, one last question. I saw someone over there.
There.
Oh, sorry. Don't worry, you have time later to speak with the speaker after the talk.
Have you considered using QEMU or any kind of virtualization or system emulation for performance reasons or software controls?
So I don't know where you are. Anyway, there. Okay.
Here, there.
Okay. So we are using QEMU. So let's say CGC binaries are in this special format. So DARPA provides you a virtual machine to run them. Nothing prevents you to run them outside the virtual machine, maybe in a modified QEMU environment. And so your question is if QEMU is putting a lot of performance overhead? No?
Sorry?
So is your question how QEMU is impacting performance?
If you use QEMU at all, and why did you not use it?
I don't have precise data about this, but I think QEMU is typically almost as fast as a normal system. I don't think QEMU is putting a lot of performance impact. And there might be specific cases in which QEMU is slow when maybe you need to emulate syscalls or of course if you want to do analysis on top of QEMU, then it might be slow. But QEMU in itself is pretty fast. And EFL is actually using QEMU to dynamically execute these binaries.
Thank you.
Thank you. Thank you, Antonio.
Okay?
So anyone willing to speak with Antonio later can